Hello, it's Keith here, and this is lesson 21 of the ChibiAkumas series of my Z80 programming tutorials. Now this episode's going to be a bit different to the other ones. We've typically been looking at stuff that's only related to ChibiAkumas itself, but this time we're going to be looking at something that was heavily used in ChibiAkumas, but we're going to look at how to use it outside of ChibiAkumas itself. So this is kind of a crossover between the multi-platform and the ChibiAkumas series. I didn't feel it was appropriate for the multi-platform series though, because we're not going to look at it on a wide variety of systems, and just depending on your requirements, this may be something that's curious but not particularly useful in your own code, but it may be very useful indeed. What we're going to look at is RLE compression. We're going to learn how ChibiAkumas compressed the bitmap data that made up the introduction and some of the other level data. So what is RLE? Well, RLE stands for run length encoding. Now, if you imagine a color bitmap like this one here, you will often see that there are strips along a horizontal line that are all the same color. For example, this part here is all purple, this part here is all black, and this strip here is all white. So we will often have repeating patterns of bytes. And even checkerboard patterns like these on and off purple pixels here, these are repeating in a linear fashion as well. Now what RLE does is it takes these patterns and it remembers them as a colour and a quantity of that colour. So if you imagine that we've got this test data here and we've got lots of 2s, lots of 1s, a 2 and a 3, we could represent this as 1 times 1 because there was just one 1 here, and then 2 times 10 because there's 10 of these 2s here, and then 1 times 8 for this section, and then 2 times 1, and then 3 times 1. And if we just counted the characters here, that would have actually reduced the size of this length. Now, of course, we don't work in characters, but that's just a sort of human readable example. But what we're going to do is we're going to learn how we can decompress RLE encoded bitmaps using the Z80 machines. We're going to be looking at the ZX Spectrum, the Amstrad CPC, the MSX and the SAM Coupe. Now, the MSX Spectrum and Amstrad versions were written for ChibiAkumas. The SAM Coupe version I ported with the plan of using it in the future. However, at this stage, I don't plan to use RLE anymore because I'm planning to cover a much wider variety of systems now. I was only planning to cover 4 or 5 systems originally, but now I'm covering 20 odd systems. So it's not going to be viable for me to convert the RLE encoder for all those systems. So I'm going to be using simpler graphics instead at this time. I mean, maybe in the future I'll port it to more systems. I really haven't decided, but it's not a priority for me at this stage. Getting a simpler game onto more systems is my priority. So how can we create an RLE bitmap? Well, the good news is I've done all the work for you. Akusprite editor, my C# based open source sprite editing program, has an RLE encoder built into it. If we go to the CPC here and File and RLE ASM, we can just save as an RLE for the CPC. We can also do the MSX here, and we can do the ZX Spectrum just here. And we also have an option in here for the SAM Coupe. As I say, the other systems do not have it at this time. Some of them may gain it later, but there's a good chance they won't, because on things like the Game Boy, it doesn't really make a lot of sense to do RLE. So I may come up with another tile-based compression routine later. That's one very strong possibility. But as I say, at this time, I'm not pursuing further systems for the RLE. And that's why this isn't in the multi-platform series. It's more relating to ChibiAkumas. So here we've got this small image here that made up part of the introduction of ChibiAkumas, and Chibi code raising hell here. And what we're going to do is we're going to compile this on various systems. So let's start off by having a look at it on the Amstrad CPC. So I'll just go to here, I will select RLE ASM, and a box says copy to clipboard. You see, this is designed to be built into other ASM files, so it tends to copy to the clipboard with the exception of the MSX version. Now if I go to this sample program here, this is just a very simple initialization to get a graphics screen running. And if I just paste in my code here, you'll see we've got some hexadecimal code here. These are the bytes of the RLE. We've got some code to load the RLE decoder and a simple drawing routine here. Now if I compile this here, and what we've got here is the RLE bitmap has been drawn to the screen. Now you'll have noticed that the drawing was relatively slow there. It's not as fast as some of the other routines that you can use, but that's the point. We're sacrificing speed for compression here. The RLE bitmaps, the compression we get varies wildly depending on the bitmap, and you can also optimize them with some tricks to make them more efficient to compress. But generally speaking, you're looking at around 50% of the file size for the RLE bitmaps for something like this. And so with regards to the introduction for ChibiAkumas, ChibiAkumas episode 2 was on 2 discs. And I really had to compress everything really as heavily as possible to do that. So that's why the RLE routines were written. I should point out these probably aren't the best RLE routines in the world, but when I wrote ChibiAkumas and ChibiAkumas episode 2, I tried to do everything myself, so if I had a choice between making my own RLE compressor or using someone else's that was better, I would always favour making my own, because I wasn't making it for the money, I was just making it for sort of personal achievement. So part of that personal achievement was seeing if I could write my own RLE compressor and decompressor. The compressor, of course, is only in C#, the decompressor, of course, is Z80. So we've seen the decompressor working there. Of course, the colours were different in this preview to that screen there, and that's because the colours aren't stored within the RLE. You would need to set them separately. And you can see here a close-up of the game over screen from Tragical Chase here, and this is what I was talking about with regards to compression. Now, as I've said, the RLEs are compressing consecutive bytes that are the same colour. So if we optimise our bitmap before we compress it to make sure there's as few single pixels as possible, then we will get better compression. For example, if you look here, I've got these small grey lines followed by these black lines here. Now, I could have done these as a checkerboard pattern with grey pixels and black pixels, but that would have been much less efficient to compress, whereas these nice little lines here are much more efficient to compress. And you can see there's relatively few individual pixels, like over here, and there's no individual pixels here, and these I've taken out odd pixels here. The effect is almost the same, but it does just save a little bit of efficiency, and that meant that this RLE bitmap could be stored in memory much easier. So when we understand how the RLE works, we know what things it can compress and what things it can't. Now, the compression does work slightly differently on all the different systems. Here's the format here. There are essentially 3 different types of compression. The main RLE one is the first type here, and the way it works is we store a single nibble, which is our RLE bitmap data, and then a count, which is the number of times that bitmap data is consecutively occurring on the screen. And this is quite important to understand when it comes to the different systems. You see, one nibble on the Amstrad CPC in mode 1 is 2 pixels. On the ZX Spectrum it's 4 pixels, and on the MSX it's just 1 pixel. So the compression works in single pixels on the MSX, in pixel pairs on the CPC, and in 4 pixel clusters on the Spectrum. Now, the reason for this is sort of intentional. It was designed originally for the Amstrad CPC and then ported to the other systems, and because the CPC was only 4 colour, I was doing a lot of these checkerboard kind of colours here where I was simulating other colours. So working in pairs meant that even if the consecutive pixels were different colours, if pairs of pixels were repeated, the compression would still work. And so that's what this was designed for. It's designed for mode 1 and these, as I call them, checkerboard patterns here, which are simulating a shade. So it was ported to the Spectrum and the MSX, but to be honest, on the Spectrum, compression isn't as important because the screen data is so much smaller anyway, and on the MSX the disks are much bigger. So while it does use the compression on all these systems, they become less essential on the other systems than on the Amstrad CPC. As well, I should also point out the Enterprise and the Amstrad CPC are virtually identical, so they use the same compression format anyway. You just need to change some slight tweaks to the next line routines. So there's no real difference to the bitmap data on the Enterprise. So our main RLE format, it has a single byte. The top nibble is the colour information. The bottom nibble is the count for that colour information. And then that count can be 1 to 15. If the count is 15, that would mean 15 consecutive pixels. But there will be times, for example, a blank screen where we need even more pixels than that. So when the count nibble is all ones, i.e. 15, we then read in another byte and add that to the count. So we would add another byte, so potentially another 255. Now, if all the bits in that byte are 1 as well, i.e. it's 255, we keep reading in more bytes until 1 isn't. So we have no limit to the maximum number of consecutive pixels that are going to be containing that RLE colour. That is up to 65535, of course, but that's not going to be relevant to an 8-bit machine. So that's our RLE data, which again is where there's a pixel pair on the CPC that are repeating over and over again. There are some more advanced options, and this was me adding things to the original RLE decoder because it wasn't efficient enough. There is something called linear bytes. These are uncompressed bytes that don't meet any RLE patterns, and so there was nothing really that could be done to compress them smaller. So what we do is we store them as consecutive bytes. The bottom count nibble of this will be 0, and so that tells the system that this isn't RLE data, this is something else. And in that case, the top byte here has the count meaning, and that count is going to be the number of uncompressed bytes to stream straight to the screen. Now, if the top nibble is all ones, again, we will start reading in consecutive bytes until we get to one that isn't 255. So again, we can have totally random data. But of course, if our data is totally random, the RLE compressor isn't going to be efficient. It's going to start wasting time and also memory. So it's only for allowing random data within a generally efficient RLE file. So that's our second format, that is random data in a chunk, and the count will be in that top nibble. Now if the first byte is entirely zeros, i.e. this part is zero, all zero, and this part is all zero, then this is an even more special kind of byte. This is a single byte that repeats lots and lots of times. So there will be, again, potentially multiple count bytes, so there will be at least one from 0 to 255, because both of the nibbles in the first byte will 0. But now, once we've got that, there would be just a single byte, and that single byte will be repeated over and over again. Well, this is for cases where, as I said, these checkerboards will compress just fine, but there will be maybe cases where, for example, there was a byte with 4 colours in it, and each one of those 4 colours was different, but that byte was repeated over and over again across the screen. There may be cases like that. So this is a way of doing those kind of compressions. Also, of course, for large black areas, this could be much more efficient for compressing. So that's the last of the compression options that my system supports. It really only supports RLE data, repeated random byte data, and repeated byte data. So that's all it is. And of course, all of this is done in C#. As I said before, Akusprite editor's free, open source. Go ahead and download it, change it, make it better, whatever you want. So we're not going to look at the source code that decompresses the RLE today. We are going to look at that in a later lesson. But today we're just going to look at how to create the RLEs and how to view them on all of the systems. So we just saw it running on the Amstrad CPC. Let's just run it again and have a little look. So you can see here we've drawn our RLE, but the system has locked up, and that's because we've got a disable interrupts and a halt here. And if we want to actually return, we need to do a little bit more work. Now, it's perfectly possible to return to BASIC, but the problem with our RLE decompressor is it's using all of the registers of the system, and the Amstrad CPC firmware relies on BC of the shadow registers not being affected. So we're going to need to back that up if we want to return to BASIC, and we can do that very easily. All we do is an EXX, push BC, pop BC, and another EXX, and then a return. So we're backing up at the shadow register BC here, we're restoring it here, and we're returning here. And now if we run this again, and now we're back to BASIC here. And of course, if we want to do our colours correctly, we need to do inc 0, 0, inc 1, 4, inc 2, 21, is it? No, inc 2, 22. Come on. There we go. And then if we would do inc 3, 26. There we go. So that's pretty much what we want our Chibi code to look like. So we do need to rebuild the color information as required. So that's how we can draw the RLE without affecting our firmware negatively. And there we go. So that's the CPC over and done with. Now I'm just going to delete this section here, and then we're going to try a different system. So this time I'm going to go to ZX Spectrum, File, RLE ASM Color. This is a color RLE file. This is a file with color information. I'll just paste it in here. Now it's worth noting that there isn't actually any color information here. The RLE bitmap, the RLE test bitmap doesn't have any ZX Spectrum color information in here. So it's all in black and white, but the theory does still stand up. It does definitely work for color because it was what did ChibiAkumas for the ZX Spectrum. So this time we're going to run on the ZX Spectrum here. And there's our Chibi drawn here with no colour. So you can see it works just fine. And of course it's faster drawing on the Spectrum because the Spectrum's half the screen space. Now once again, if we want to make sure the firmware is unaffected, we do need to back up, I think it's the IY register on the ZX Spectrum. But it still does work perfectly fine. It was used during the loading sequences of ChibiAkumas on the Spectrum, so I can assure you it does work just fine. So there we go. That's how we can do it on the ZX Spectrum. And so this time let's try the SAM Coupe. And so as with the Amstrad and the Spectrum, it's copied to the clipboard. Now if I do a paste here, now there's more data because this is a 16 color system. And then if I run again, you can see here we've got our ChibiAkumas bitmap here. But again, the colors are wrong because the colors aren't stored within the file. So there we go. So that's the Sam Coupe. And now what last but by no means least, we have the MSX. Now if we select RLE here and save MSX RLE with palette and save it here. Now you'll notice this time we're actually saving a file. There's a good reason for this, because in most cases, rather than loading from memory, I was streaming straight from the disk. The reason for this is very simple. The MSX has a 24 kilobyte screen and only 64 kilobytes of memory. And also the disk system is actually relatively slow, so in most cases it's quicker to decompress the RLE than it is to load uncompressed data from the disk. So in all cases, compressing and streaming from the disk made more sense. But that said, we are able to simulate the disk load by streaming from memory, and that's what we're going to be doing here. So we're using this program to decompress from memory. We're including our RLE file here and our RLE decompressor here. And we've got this dummy label here, which is just to allow for the streaming code, which usually works from disk, to work from memory in this case. And now if we run this, and there's our ChibiAkumas drawn to the screen, and you can see the colors are correct because we saved the color information in the file. The MSX is the only system that can save colors into the file. So there we go. So we've seen our bitmap drawn on all of the systems. Now the format of the data is slightly different in each case. On the MSX we are storing an X and Y position here and the source and destination of the data there. On all of the other systems the command is following a different format. We have the start of the data, the end of the data here, -1 in both cases, a vertical Y line to start drawing, the width of the data, and the right hand side of the data. Now the data draws from right to left. It was designed to work with stack abuse. It doesn't actually use stack abuse as it stands, but it was designed to work with it. That's where you use the push command to write data quickly to the screen. So it actually draws right to left rather than the more logical left to right, but that's the way it works. Now here's the CPC version, and you can see we're running a setup routine here which gets our definition, and then we're calling our RLE draw routine here. Now, the reason we work like this is the way that ChibiAkumas worked when it was getting its data in. It had a routine that would get the settings set up, and then it would call out to a common routine that would draw the data. Anyway, we're going to be looking at the actual source code that does the work in a later lesson. I just wanted to introduce the concept of the RLEs and show you how you could use them in a simple way in your own code. So as I say, if you like what you saw today, please download Akusprite editor, and you can also download this source file. It's called RLE test, and you can just paste in as you just saw me do, and you should be able to compile working RLE files with these tutorials. Hope you've enjoyed this. If you want to see the next lesson, please subscribe so you catch when the second episode of this RLE series is done. Thanks for watching today, and goodbye.